So today we want to talk about principal component analysis. This is one of the two lectures on feature extraction or feature analysis. So here is the outline of where we are in this part of the course. Last time we talked about linearly separable, this concept. We draw some pictures, we draw some lines, we define the distance between a data point and the plane, and then we talk about a separating hyperplane theorem. We show that if you have a set that contains two classes of data points, and then if they're convex, they satisfy certain conditions, then you know that they are linearly separable. But of course, in reality, as all of you know, that the world is not perfect, and so we are living in a nonlinear world, and so many of the data points that we encounter every day, they may not be linearly separable. And so today we want to talk about the methods that not necessarily turn them into a linearly separable situation, but if the input data, the raw space, it does not facilitate a simple classification algorithm, maybe we want to do something to turn it into another space so that in the new space it's easier. Examples would be like I give you an image, and then you chop the image into small patches, and then you're looking at the pixel domain. And then the pixel domain will become red, green, and blue, the three color channels. And then you may have 100 or 200 pixels in that small patch. How are you going to run classification algorithms? Well, it may not be that easy because now the dimensionality that you're handling would be very, very large. So then we typically do would be turning into the discrete cosine transform domain, DCT domain, or turn it into the Fourier domain, turn it into the wavelet domain, and then look at the few leading coefficients in those spaces. And then perhaps, one, you can reduce the dimension. Two is that maybe with a lower dimension, you can have an easier algorithm to classify the objects. So principal component analysis is one of that kind of tools, okay? So in this lecture 7, we're going to look into what is PCA, things you may have heard before, but if not, it's also a good time to learn about this idea of PCA. It's very useful. Then next time, we will talk about something you will definitely like. It's called deep neural network. Okay. Now, I am going to not teach you deep neural network as an object itself. I want to pull the deep neural network into smaller pieces, and then put them into the right perspective of what that piece is actually doing in the deep neural network. And then in next lecture, lecture number 8, we will see that in fact, many of these deep neural networks, at least the first few layers, what they're doing is that they're trying to pull features for you, just like the PCA. Okay, so PCA is pulling features, finding low-dimensional representations of the data. And deep neural networks, the first few layers, they're also doing similar things. You pull the features. And then at the end of the deep neural network, you are going to run some classification. And in many cases, those classifications are based on linear classifiers. Okay? So once we have that perspective in mind, when you look at the deep neural network, it's no longer a very complicated object. All right? It will be multiple modules inside the deep neural network. Each module is functioning for certain tasks. So that would be the plan for lecture number 8. Now, for today, we want to look at this concept called principal component analysis. It is very widely used in almost every data science problem. That can go to medical data, that can go to image analysis. It's just very broad. So we want to understand the basic ideas of PCA. Again, we want to draw some pictures. We want to explain the geometry, and then I want to show you a very practical application of PCA. It's called the Eigenface problem. Then the remaining half of the lecture, we will talk about something called a kernel PCA. It's like an extension of the kernel method that we learned in the linear regression setting, but we want to put it into the PCA setting. So now this kernel is no longer just a kernel itself. It can be used to multiple places. As I promised, it will be used in regression, it will be used in PCA, it will actually be used in a support vector machine. It can be used in multiple places. So we will talk about that. Okay, so the starting point of this principal component analysis is the following question. I have data sets that contains points x1 through xn. I have n data points. I know that these data points, they are living in high dimensional space. By high dimensional space, I mean that the ambient dimension of all these vectors is RD, and D could be a very big number. So think about an image, and then the image you have 100 pixel by 100 pixel, that is 10,000 dimensional variable, right? So that would be the intrinsic dimension. So we want to find a low dimensional representation in RP, where P is much less than D. Okay, so think about, now you have 10,000 variables. It will be 10,000 dimensional vector. I only want to use maybe 10 or 20 bases so that I can represent it. Now the question goes the following. Then how do you find the bases? How do you find the coefficients to describe the bases? So we want to look at those problems. And so equivalently, what we mean is to find the principal components V1 through Vp such that your x, this is your input vector, can be approximately written as a linear combination of your basis vectors, and then these are the coefficients. You want to sum them up. Okay, so you want to find alphas, you want to find the v's. And so this is a picture. Let's say we have a group of data points. They are marked by the blue crosses, and then their distribution have this kind of shape. By principal component, we mean that we want to find the first principal axis, which will capture most of the variation along the axis. And then there will be an orthogonal axis, which is orthogonal to the first axis, and then that will capture the second direction. That also capture the variance of the signal. So to talk about this pre-CA, I want to start by illustrating an extremely simple problem, and then we can build from this simple problem onward. The problem is the following. Suppose you have one data point, okay, just one. Imagine that you only have one data point, and then you want to find one direction V to describe that. Now, you will say, okay, one point that would be, and then one direction, the direction would be that point. Okay, so bear with me for a second, okay? What I want to do is the following. I want to solve a minimization problem like the following. You have your input vector x, and then you want to write this x as a linear combination of alpha and v. Now, I am on purposely writing in this way because you can generalize this formulation to have more alphas and more v's later on. Okay. Now, of course, this problem itself is useless because you only have one data point, and you know that would be the solution. It looks trivial. Okay. But we still want to go through this exercise and then see if we can generalize this idea. Okay. So suppose you want to solve this minimization problem, and let me tell you that this v is already fixed. Okay, so I give you a data point, which is a vector, and then I also give you the v vector, which is a direction, and then I ask you what would be the alpha that can minimize this distance. This is a well-posed problem, okay, only of one variable, okay, and then you want to find that scalar such that this x will be as close to your alpha times v as possible. So how do you do that? It's very easy. You look at this expression. This is a quadratic equation. You take the derivative with respect to alpha, right? So this is a quadratic form. You take a derivative with respect to alpha. You get v transpose x minus alpha v. You set it to 0. You get the solution. Alpha equals to v transpose x. Does it make sense? It makes sense because v is what? V is the direction that you have picked. And then x is your data point. What is the meaning of this v transpose x? That's the inner product. That's the projection of your blue vector onto the direction that you are given. So you're doing this projection, and this length is v transpose x. That will define your alpha, and that will be the best alpha that you can use. All right? So this is very simple. It's one data point, and then I tell you the direction, and so I ask what would be the corresponding alpha. Now, the second half of the problem is the following. So now you have the alpha. Can I ask, okay, what would be the best direction v? Now, it turns out that to solve this problem, what you need to do is to go to this objective function, and then you can expand. This is a quadratic term. Expand it. Then you have x transpose x that comes from the first term, 2 alpha x transpose v that comes from cross term, and then alpha square of v transpose v that comes from the third term. And since we do have a constraint here where the 2 norm of v equals to 1, that's an arbitrary constraint I put, so that your direction is unit norm. Now you don't have to put it, but putting it just makes your life easier. Well, if you make that assumption, then the third constraint, this v transpose v, this term will go away because you assume that the 2 norm of v is 1. So then you were left with this equation. Then going from here to here, you ask, where does the x go? The x is gone because you're doing minimization over the v. X has nothing to do with the v, so you can remove that. Then you can plug in the alphas. All right. So here you have the alphas. What is alpha? Well, alpha is just x transpose v. Right. So that is your alpha. So plug that in. Then you rearrange the terms. There you have -2. Here you have +1. So you end up having minus. Okay. So when you take the sum of these two, you will have minus x transpose v square. And so since you are minimizing this function, it is equivalent to taking the maximum of the term without the negative sign. So you can switch the minimum to maximum by removing the negative sign. So at the end of the day, what do we have? Well, you have this problem. Okay, you have this problem. Now again, this is a one-point problem. There's nothing interesting because there's a trivial solution that v has to equal to x. But suppose you take the expectation of x. Okay, now imagine that you are no longer just having one data point. Let's say you have a set of data points. The set of data points x, that comes from certain distribution, and so now you can take the expectation. Before that, you're trying to minimize that 1 point 2 norm difference. Right now, you want to minimize the average across all the possible data points that you have in your data set. So you put the expectation here. That means you're putting the expectation inside, right? So when you look at this term, this is what? This is the expectation of x transpose x. That's also the covariance matrix, assuming that the x vector has 0 mean. So that's the covariance matrix. And now if you look at this problem, what is it? There's a quadratic minimization with the direction having constraint that the norm is 1, and then you want to find the v such that this is maximized. This is equivalent to an eigen decomposition problem, if you can recall. Okay? Now, to be slightly more precise, I want to define the following notation. So I'm going to define a sigma equals to expectation of x transpose. Then the previous optimization problem will become this. You are going to do this arc mean on v transpose sigma v, and then you have this 2 norm of v equals to 1. You have a constraint minimization problem. It turns out that, according to this theorem, that the solution of this problem is given by the eigen decomposition of your sigma matrix. By that I mean that first you take the eigen decomposition of sigma, you will get U and S and U transpose. U is the eigenvector matrix, S is the diagonal eigenvalue matrix. Then the solution to this problem will be any of the eigenvectors. Okay, depending on which eigenvalue you want to pick. Okay, so here you may say, oh, okay, I only want to pick the first one. Then it would be U1, the first column of that U matrix. That will return you the eigenvector. And any eigenvector coming from here will be a solution to this problem. All right, now the proof, I will leave it to the appendix, and you can read it by yourself. It's just some very standard Lagrange multiplier type of a solution. What you will get is that the solution has to satisfy the condition that sigma times v will equal to lambda times v. Lambda is the eigenvalue of the sigma matrix. Okay, so you will have this equation here. Okay, so why do I want to introduce this expectation perspective? Is because of the following. When you have a data set, let's say you have n data points, the n data points that you have is a finite approximation to the entire data set. So by taking the expectation of this quantity, okay, so now, okay, let's look at this equation here. On the right-hand side, you have this summation of n going from 1 to capital N. This is the number of training samples that you have in the data set. And this 2 norm square, that measures the distance between your data point and also your vector. The situation would be that you have 10,000 data points, and then here is one direction. I want you to project all these data points onto that direction. I ask what would be that direction, that common direction that can capture all these n data points. This is the meaning of this optimization problem. And now, if you send the limit of n going to infinity, then you are essentially taking the expectation over all the possible x to solve this problem. Then equivalently, on the right-hand side, the problem that you're solving is that you can look at the inner matrix. This is the empirical covariance matrix. And if you send n going to infinity, that will give you the expectation of that X transpose. All right? Okay, so the reason why we want to study this extremely simple problem is that it's extendable. It's extendable to many, many data points. I give you many, many data points. I want you to find one direction. That will be the solution, is to solve this eigenvalue system. In practice, of course, you do not have access to this expectation of X transpose. So what you do is that you calculate this empirical covariance and treat it as the covariance, and then you find the eigen decomposition of that, and you using the eigenvalues, eigenvectors there as your principal component. Okay, so now the last comment here is that you can also remove the mean if your X vector is not zero mean. Then this the new definition here with the mean subtracted, that will give you the real covariance matrix. Otherwise, this is actually called a correlation matrix. But if it is zero mean, they're the same. Okay, so there is some statistical interpretation of the method that I just described. So when you're trying to solve this problem, because the sigma matrix is the covariance matrix, and you want to maximize this quadratic quantity, you're essentially picking the direction that has the maximum variance. Now, what I mean is that you look at these data points, you have the blue crosses. If I pick this direction, let's say the horizontal direction, I ask myself, is it going to maximize the variance? Okay, is the variance going to be maximized along this direction? And clearly it is not, because you have the maximum variance goes along this direction, right? And therefore this is not the principal component, this is not, and this is the principal component, because now you're looking at a direction that has the maximum variance. By variance mean that the deviation from the center. Okay, so you want to have the biggest deviation towards the center. So that's the statistical interpretation. Now, how do you actually use this principal component analysis? It's actually very simple. You grab a data set. I give you a data set, all right? And then these are high-dimensional data points. They're all vectors. You grab them, and then you turn them into a data matrix. Okay, you turn them into a data matrix like this. Okay, so you have all the x vectors, and then you take the outer product, and then you sum them up, divide by the total number of samples to form this covariance matrix. And then what? Well, and then you calculate the eigen decomposition of that sigma matrix, and then you keep the leading eigenvectors, and then you're done. All right? So by keeping the leading eigenvectors, these leading eigenvectors will be your principal components, and then to get the coefficients, you should just take the inner product with your data point, and then these principal components. So let me illustrate this idea through an example. This is one of the most classical problem in computer vision. It's called the eigenface problem. The problem is that you have a set of images, and then these are denoted by xn, where n goes from 1 to n. They are the d by d images, square root d by square root d images. And then you want to find a low-dimensional representation of these images. Now, each image itself, it is a vector. It is a high-dimensional vector. It could be a 100 by 100 pixel image. I want to use a lot fewer numbers to describe that image. So what I can do is that I can form the covariance matrix. Right? So now you have all these mean vectors, mu. I can first compute the mean vectors. So that means I grab all the images, I calculate the average of the entire data set. So you have image 1 and image 2, you just add all these images up, divide by total number of images. That would be the mean vector. This itself is an image. Okay, it has a dimension of an image. Then you calculate this covariance matrix. So you form this empirical sum. Then you do the eigen decomposition of this sigma. You keep the leading eigenvectors. Okay. So now if you just do this eigen decomposition, you will have a very, very big matrix. Okay. So then you will say, okay, I only want to keep the first maybe 10 or 20 leading eigenvectors. These will be your principal components. Then you calculate this projection, this alpha. Alpha is the inner product of your data point y. So now I give you a new image and ask, can you give me a low-dimensional representation of that? Then I will just take this inner product for all the i's that I have. So this I will denote the number of the index of the eigenvector. And you can ask, okay, how many eigenvectors should I actually keep? The simplest way to do this analysis is that you can plot the eigenvalue of this S matrix, and you can look at the spectrum. Okay, so this x-axis is I is the eigenindex, y-axis is the value inside this S matrix. You plot it out. Typically, you will have a few very, very big eigenvalues in this matrix, and then the rest, it will go down and then eventually go to 0. Okay, so that would be a distribution of all these eigenvalues. Then you can make a decision. I want to keep 90% of my energy. That means I want to go down this curve so that this cutoff point will correspond to maybe 90%. Okay, the rest maybe correspond to 10%. So you can do this kind of calculation to decide how to stop the eigenvectors. Normally, maybe between 10 to 100, that would be the typical number that you're aiming for, depending on the ambient dimension. Right? So you want to play around these numbers, making sure that you do have a reasonable representation, and you stop there. Here is a snapshot of the eigenfaces. Now, they may not mean too much to you because they are just some results returned by the computer. However, you do realize a few things. One, each of these, they are the bases. Okay, so they are the eigenvectors. Of course, I reshape them to show you the image looking of these vectors. They themselves, they are images. And then this is the first eigenvector. This is the second eigenvector. And interestingly, if you take the inner product of any pair, you will get 0 because they're orthogonal. Okay, so this eigenvector and that eigenvector, when you take inner product, they're 0. Also, you realize that actually any image, you give me image, I can represent it as a linear combination of these eigenfaces, these basis functions. So what I mean is that suppose I give you a testing image, which it doesn't come from your data set. So you first train your eigenface basis function, and then now you have a query image. It looks like this. Then I ask, can you give me a low dimensional representation of this image? Rather than using 100 by 100 pixel to describe this image, can you give me maybe 20 coefficients to describe this image? Now, how I can do is, I go to my basis functions. Right? So each one will correspond to a vector. And then I can calculate the inner product to get my coefficient. Because these alphas, they are just the inner product of y and the u's. Then I can get these coefficients. Then what do I need? At my classification stage, I do not need to have access to this U anymore. I just need to keep the alphas, because these alphas, they are the features, right? So I just need to keep these features as my input to my classifier. Rather than dealing with a 10,000 dimensional vector, here I may just need 20 numbers in this vector to do the classification. Of course, this is a lot easier problem than before, right? So you can effectively shrink the dimensionality from a high dimensional problem to a small dimensional problem. That is the purpose of this PCA. So what does PCA do? Well, PCA is a tool for dimension reduction. And the goal is to compress a raw data vector Y in RD into a smaller feature vector alpha in RP. With the goal that, of course, P is less than D. And then now you can do classification in RP instead of doing things in RD. It's a lot easier. Now, when will PCA fail? PCA is not perfect. Okay, although people have been using PCA in many, many different occasions, PCA is not perfect. It fails when intrinsically the data points, they do not allow you to have this orthogonal projection. For example, like this. You find the maximum variance direction. It will be here. That will be your U1. The U2 should be there. However, because you're stuck with this PCA, you're stuck with this orthogonal projection, the best you can pick is this U2 orthogonal to U1, right? So there's nothing that you can do with the PCA in situations like that. So there's another line of work called the ICA, Independent Component Analysis, that will give you some tools to handle situations like this. I have one direction, I have another direction, and then the two directions, they are not necessarily orthogonal. So that belongs to another branch of work. Now, there are also other methods, like what we are going to talk about, is the kernel method, that can help you handle situations like this, because intrinsically the data points, they are not distributed in such a way that you can run the linear analysis. So perhaps some kind of a kernel method will help you solve the problem. Now, of course, there are other issues associated with the PCAs. One issue is that suppose I am working on a data set that contains some medical information. So that can be height, that can be weight, that can be your BMI, that can be sugar level, or something like that. And so you say, hey, I want to do this principal component analysis. I want to find the main components. I don't want, maybe because some of them could be overlapping. I just want to get the orthogonal basis. Once you do that, the meaning of that orthogonal basis is unclear, because you find orthogonal basis. Is it the sugar level anymore? Is it the BMI level? Is it the height? Is it the weight? You will lose the interpretability when you go to the PCA domain. Just like the eigenface I showed you, do they carry any meaning? It's arguable, right? Because the meaning is not there. Another issue is that sometimes when you work with data sets, that you may have one vector, okay, one type of features that has very, very large value, okay? And then some other feature vectors, they may have very, very small values. For example, you're measuring the temperature, and then the other one you are measuring the speed. Okay, it could be that and then you're measuring in the meter per second in that kind of scale, and then the temperature you're measuring in some of the scale. There's a scale they do not match. One is very, very large, one is very, very small. So when you just run a raw PCA, and then you say that, oh, one component is much, much bigger, that could be misleading, because it could be coming from your original data set, that one scale could be originally much, much better. So there's also some kind of renormalization, pre-processing of the data that you need to take care of when you run PCA. One more issue that you may encounter is in some problems, you may want to remove the mean. In some problems, you may not want to remove the mean to do a PCA, because both are okay. Okay? So in some of the signal processing problems, you do want to run the PCA without taking the mean, so that you can capture the mean behavior. But in some of the medical analysis, you do want to take out the mean because the mean could be harmful to your analysis. So whether you want to take the mean out or not, that's another open question in the community for some time. That's actually a paper that I put at the back of this lecture slides that talks about whether you should take a mean or not. Okay, so there will be discussions there. So I think that PCA is a very, very popular tool out there, but there are also some issues that you need to be aware of, especially when you have your own data sets. Try to ask yourself a few questions, like is this data set is PCA the right tool to apply to this data set to draw the principal components? Do I need meaning of these principal components? Yes.
You have a question. You go back to the previous one. So you're saying there are a bunch of situations which the PCA cannot actually work very well. I know it's in 2D case, it's easy to tell from the ground, but if it's in higher dimension, will there be any algorithm or any formula that can help us to tell if this set of data can be used by the PCA?
Okay. So the question is that if this is a 2D, so I can plot it out, and then I know whether TPCA is good or not. Now in high dimensional space, how do I know whether the PCA is working or not? Well, what you can do is that you actually run the PCA first. You run the PCA. Now, if the PCA is working well, you should have the eigenvalues go down to 0 very, very quickly, because that means the few eigenvectors, they are sufficient to capture a lot of energies. However, if the PCA is not working, then this eigenvalue will spread out. Then you know that my PCA is not working very well.
And when you're talking about a cutoff, are you meaning that the area below this graph, or below the curve, or are you meaning the eigenvalue?
So what I mean is that the area under the curve, because the area under the curve will capture the energy of your basis, right? So if because here you have height here, you cannot just measure the height. Okay. Now, of course, you can say I only care about the height. I want to cut off a certain magnitude. That's easier solution to me. But normally, what you would do is that you know that the energy is preserved in the PCA space, right? Since energy is preserved in the PCA space, I want to keep 90% of the energy. So what I do is that I look at the spectrum. I sum the area under the curve until 90% of the curve is covered. Then I cut off there. Right? That will make sure that the 90% energy is captured. If you cut off according to the magnitude, that is harder, although you can do it. Computationally, that's easier because you don't need to do anything. But in terms of the interpretability, that would be somewhat limited, in my opinion, because it's just hard to say that cutting off at here would be a good choice without any statistical information. Because if I cut there, I want to make sure that that only contains 10%. So that can be a consistent cutoff for all the data points or all the data sets that I'm working on. But if you're trying to cut off according to that y-axis threshold, when you change from one data set to another data set, you need to change that threshold. So that is less helpful.